Time travel, a concept that has captivated our imaginations for generations. From H.G. Wells' The Time Machine to the iconic DeLorean in Back to the Future, the idea of journeying through time has fueled countless stories. But what does science have to say about the possibility of actually bending the river of time? Could we one day build machines that transport us to distant eras? While the technology for time travel remains firmly in the realm of science fiction, the fundamental laws of physics do not explicitly forbid it. In fact, there are aspects of Einstein's theories of relativity that suggest time is not as rigid and unchanging as we might perceive it to be. To understand how time travel might be possible, we need to delve into the fascinating world of modern physics. Let's embark on a journey to explore the science behind time travel, separating fact from fiction. We'll examine the mind-bending concepts of Einstein's relativity, the role of gravity and speed in affecting time, and the tantalizing possibility of both forward and backward time travel. Prepare yourself, for the universe holds many secrets, and the nature of time is perhaps one of its most profound mysteries. If you enjoyed this dive into the mysteries of time travel, make sure to subscribe to our channel, hit the bell icon, and like the video for more fascinating explorations. Our everyday experience tells us that time marches forward at a constant pace. 1 second feels the same to us regardless of where we are or how fast we're moving. However, this intuitive understanding of time is an illusion, a simplification of a much grander reality. Einstein's theories of relativity, formulated in the early 20th century, shattered our classical view of space and time as separate entities. Einstein proposed a revolutionary concept. Space and time are not independent but rather interwoven into a four-dimensional fabric called spacetime. Imagine a vast, flexible sheet. This sheet represents spacetime, and objects with mass, like stars and planets, create curves and depressions in this fabric. This curvature is what we experience as gravity, but Einstein's insights went even further. He realized that not only does mass warp spacetime, but so does motion. The faster an object moves through space, the more it affects the flow of time in its immediate vicinity. This is where the concept of time dilation comes into play, a phenomenon where time actually slows down for objects in motion relative to a stationary observer. Time dilation, a consequence of Einstein's special theory of relativity, states that time is not absolute but is relative to the observer's frame of reference. This means that time can pass at different rates for observers who are moving relative to each other or who are experiencing different gravitational fields. Imagine two identical clocks, one remaining on Earth and the other traveling at incredibly high speeds through space. Upon the traveling clock's return to Earth, it would show a slightly earlier time compared to the clock that stayed put. This isn't a mechanical malfunction, it's a demonstration of time dilation. The faster-moving clock experienced time at a slower rate due to its high velocity. Similarly, gravity also influences the flow of time. The stronger the gravitational pull, the slower time passes. This effect, predicted by Einstein's general theory of relativity, has been experimentally verified. Atomic clocks at higher altitudes, experiencing slightly weaker gravity, tick slightly faster than their counterparts closer to Earth's surface. If you enjoyed this deep dive into the science of time travel, make sure to subscribe to our channel for more fascinating content. Hit that subscribe button now and join our community of curious minds. Perhaps the most extreme example of gravity's influence on time can be found in the vicinity of black holes. These cosmic behemoths possess gravitational pulls so intense that not even light, the fastest entity in the universe, can escape their clutches once it crosses a boundary known as the event horizon. If an observer could survive a close approach to a black hole, a feat impossible with current technology, they would witness time behaving in truly bizarre ways. From the observer's perspective, time would appear to slow to a crawl for objects falling into the black hole. Conversely, to an observer far away from the black hole, the infalling object would seem to freeze in time at the event horizon. While black holes represent an extreme case, they illustrate the profound connection between gravity and the passage of time. Time, far from being a rigid metronome ticking away uniformly throughout the cosmos, is a dynamic entity, intricately linked to the fabric of space-time itself. This realization opens the door to the tantalizing, albeit highly theoretical, possibility of time travel. If you enjoyed this exploration of black holes and time warps, make sure to subscribe to our channel, and hit the bell icon for more fascinating content. Don't forget to give us a thumbs up.